Yep. So all we're going to do now for the next probably week and a half, honestly, this takes a while, is work with complex numbers. And so today is the 11th. Oh, I don't want to start my notes in red. That's bad juju. So today is the 11th. And overall, the goal for today is to do graphing and absolute value. Of complex numbers. And I think, if I'm not mistaken, that in Delta Math, they will refer to the absolute value as the modulus. Just so you know, so that when you see that word modulus, you can just kind of think, oh, absolute value, like we learned in class. So yeah, I guess before we start, I was trying to think this morning about what words I wanted to choose. I always think about like, what would make this the most sense to me? So I would be remiss if I just dove in and we didn't talk about what a complex number is. So this is a good time now to show you what the whole number system looks like that you've ever worked with. I'm not very good at these Venn diagram kinds of things. You've seen them before. But every number, essentially every number that exists is in a big set. Sorry, if this part confuses you, just tell me and I'll slow down. There's a big set of numbers. It's basically all numbers that exist. And every number in the known universe is referred to as a complex number. You've never heard them referred to, you've never heard them be referred to as complex numbers before. That was hard for me to say. So there are two things that happen. Basically, everything is a complex number. And then there are two subsets of the complex numbers. And one of them is a little set over here that you've worked with for basically up until about a week ago or so, every number you've ever seen. And those are called real numbers. So that's one subset of the complex numbers. And then another subset of the complex numbers are what we call pure imaginaries. And if you don't get much out of this part of the lesson, quite frankly, it would be okay, because I just want to make sure that if for anyone who's interested in what in God's green earth is a complex number, that you can get your head around what I'm talking about. And but again, it'll come to you when it's time if it doesn't work today. So complex number, I need to define it for you now. And I'm not going to give you like a formal wordy definition, but complex numbers are like this. A plus BI. Get used to seeing things that look like this. It's going to be your entire existence in this class now for the next like 4 or 5 school days. Things like 3 minus 4i, negative 6 plus 5i, 10 minus 3i. Those are all what we call complex numbers. And A and B, when I write A plus BI like that on the board, A and B are just normal numbers. You know, they're like 2, negative 1, whatever. That doesn't matter. But there's two parts to this. There's the A part, which is what we call the real part. And then there's the BI part that we call the imaginary part. I think it's obvious because it's got the I with it, right? So you have a real part and you have an imaginary part. So if you think about the subsets, and you don't have to answer this right, I won't judge, but to be a real number, what would you look like? Like if all complex numbers are A plus BI, what's a real number? What doesn't it have? No, it's not about variables. So like, here's an example of a complex number. Here, let me just put one up here for you. We'll just fill in our little diagram. Here, there's a complex number, 5 minus 6i. Here's another one, 3 minus 4i. Here's another one, 10 plus I. Here's another one. Say it again. It's not about negatives. It's the I. It doesn't have an I. To be a real number, i.e. every number you'd ever seen until a week ago, to be a real number, you don't have an imaginary part. If you do, you're no longer a real number. So an example of a real number would be something like negative 6, 2/3, 49, 512.3. Those are all examples of real numbers. You could even put a square root, like the square root of 5. As long as it doesn't have an imaginary component to it, then it's what we call a real number. The other ones are what we call pure imaginary numbers. What do you think those don't have? If you're purely imaginary, what do you not have? Say again? Here's an example of a pure imaginary. Let me put one in here for you. 10i. You don't have a real part. Very good. So listen, complex numbers have, generally speaking, two parts. They have an A, which is the real part, and they have a BI, which is an imaginary part. But if you're in one of the subsets, then if you don't have your imaginary part, you're a real number. If you don't have your real part, you're what we call a pure imaginary. And another example of a pure imaginary could be something like -6i, 42i. Those are all pure imaginary numbers. I mean, there's no nice way to get this stuff isn't supposed to make sense the first time you see it, but the complex number system is everything. Everything. But it can be broken into little subsets, if you will, of more specific variations on the complex number theme. So the reals don't have imaginary parts, and the pure imaginaries don't have real parts. But most honestly, of the numbers that we're going to talk about for the next a week or so are going to be these guys. That's just the standard complex numbers with both parts. Okay. Apologies if that's confusing as all get out, but there's really no, despite my best efforts to choose words, there's no real nice, sweet way to get through that. So that's not the important part of the lesson. Can I help you? Can we go down? You have to go. If you have to go, you have to go. Can I ask something of you though? Will you please promise me that you'll watch this video and get the homework done like everybody else? Yep. Yeah. Okay. You know, we were recording just now, so I got your promise on recording. Jackpot. So apologies again for that part of the lesson. It just, you got to get it done, and then we can move on to what we're doing today. So the first thing we're going to do is we're going to look at complex numbers, and complex numbers can be graphed in what we call the complex plane. And you've been graphing since you were in like probably 6th grade, I think, is when you probably started graphing. Like, you remember how your teacher would say, okay, graph the point 4, 2, and you all figured out to go right 4 up 2 and put a dot. So it's like that, but the complex plane does not have an x-axis and a y-axis. So the complex plane consists of axes, as you would expect, 2 lines, yep, an axis and another axis, but they are not called x and y. This is called the real axis, and this is called, as you would probably guess, the imaginary axis. You're about to learn one of maybe the 3 easiest things that you will learn all year in this class. So as difficult maybe as that first clumsy part of the lesson was to understand, this will be on the dead polar opposite end of the does it make sense spectrum. So there's no way that this next 5 minutes doesn't go well. So I'm going to put a complex number up here, and we're going to graph it. And so here's a complex number, 4 minus 2i. And if you're already thinking, could this be as easy as I think it is? The answer is yes, it is. While I pour myself some coffee, would anyone like to just throw out a guess as to how we graph the complex number, Brady? That's it. So the real and imaginary components of the complex number just dictate where we go to put our dot. And they're just dots. We're just graphing points in the complex plane in the exact same way that we would graph points in the real number plane, in the normal XY plane. So I'm going to simply go to the right 4, and I'm going to go down 2, and I'm just improvising, like I'm not sure on my distances, but bam, that's it. I just plotted a complex number in the complex plane. All right, let's go again. How about -6i? What do we call that, by the way? What is -6i again? What's his name? He's a pure imaginary. Nice job. Where will we find him? At just down 6. Very good. So pure imaginaries are found on the imaginary axis. And what if I asked you to graph something like -5? What is that called again? That's a real number. It's a complex number, but it's a real number. And so I just go where, Patzer? I just go left 5. So points can appear in the complex plane in any of the four quadrants, or of course on the axes as well. Reals appear on the real axis, pure imaginaries appear on the imaginary axis. Is there any chance at all that that part doesn't make sense? Okay, so that'll be half of your assignment. Believe it or not, you're going to go through Delta Math and it's going to ask you to plot complex numbers. And you're like, okay, jackpot, I think I could do this. The second half of today's lesson is finding the modulus or the absolute value of a complex number. And this one is just some real basic geometry sort of stuff. You guys remember from geometry the thing called the distance formula? Or do you maybe remember the Pythagorean theorem? Would you believe me if I told you that the distance formula and the Pythagorean theorem are literally the exact same thing? You know, the Pythagorean theorem says that a squared plus b squared equals c squared, right? You know that? Mr. Manlove, what? Oh,
So we're back.
welcome back. Yeah, I mean, he says super easy. He's not being facetious. It was real easy. So the last part of this today, and this will be the one that we will spend the most time on, is finding the modulus, or the absolute value. And the absolute value, by definition, is how far the number is from the complex origin. And the complex origin is, of course, right here, correct? That's dead center. That's like ground zero. Now, what we're going to do is we're going to find distances to points. So if I wanted to know the modulus of the pure imaginary number -6i, the notation, guys and gals, here it comes again. Sorry, we're coming back like a flashback, would look like that. The absolute value of -6i. And this is a question, honestly, don't feel stupid, but I should be able to ask this to a fourth grader. And if they weren't confused by all the I's and stuff, if I just said, hey, kiddies, how far is it from the center to get to this yellow dot? What is the answer? Done. So you just found your first modulus. You just found your first absolute value of a complex number. It's literally the distance that you have to travel to get there. If you have a number that's on the imaginary axis or on the real axis, math doesn't get any easier than that. It's like count. You don't have to like count. You just look. And so if I said, what's the modulus or the absolute value of -5, what would you say? It's 5. I can see it. I can see it's a distance of 5. So where we spend the most of our time today is in talking about the modulus or the absolute value of a complex number that's not situated conveniently in a horizontal or vertical direction. So let's talk about the red point. So sorry for the geometry lesson, but not sorry for the geometry lesson. We're going to find the absolute value of the point 4 minus 2i. And to get there, what we have to consider is that the distance to get to the red dot is going to look like this. And I've drawn a triangle here for a very specific reason, and that is because whether you've taken geometry or not, at some point in your life, you've been exposed to a squared plus b squared equals c squared. It's just inevitable. Like, so at some point, someone in your life has brought it up to you. And so this, of course, we know is a right triangle. So there's a little right angle right here. And how long is this side? I can count that. What's the top side? It's 4. I know that for a fact. And how long is my vertical drop? Just 2 is fine. So distances, remember, you're fine. You're fine. It's down 2. I get that, but it's just a distance of 2. And so if I wanted to know the distance from the center to the red dot, then I'm going to do a squared plus b squared equals c squared. This, let me kind of put some marks on it for you so you can see. That distance that I'm notching off with some little tick marks, that's of course c, right? That's always the c in a triangle like this is always the hypotenuse, the side across from the right angle. We okay? And then of course, Gavin, you okay? Are you sure? So what's 4 squared? And what's 2 squared? Okay, and what's 16 plus 4? So if c squared equals 20, c is not 10. C is equivalent to then the square root of 20. If you think about it, like if I say to you that I got something squared that equals 20, then the something by definition has to be the square root of 20. Like, let me give you a simpler example. I'll write it in blue. If I told you that I was thinking of a number x, and when I squared him, I get 100, you would logically assume that the number I'm thinking of is 10, right? Because 10 is the square root of 100. You agree? So 20 can't be so conveniently square rooted as 100 can, and that's why I express it just as the square root of 20. So what I can say right now at this point is that that distance, that hypotenuse right there, is exactly equal to the square root of 20. Now, we don't like that answer. Why? Because it can be broken down, simplified, however you want to say that. So I'm going to break down my square root of 20 into the square root of 4 and the square root of 5. And remember, it's not a 4 and a 5. It's a root of 4 and a root of 5. So what answer would I type in? That's it. So we can say that the modulus, or the absolute value of the complex number 4 minus 2i, equals exactly 2 root 5. That's its physical distance from center to him. Okay. Let's do another one. Let's find the modulus of -3 plus 4i. So for the purpose of this lesson, so I can do one more. After this, we probably won't draw any more pictures. There's a much shorter way to do this. So for the purpose of this, to get to the point, where would I go? Yeah, I love it when people don't say over. Thank you so much. Left 3, up 4. You cannot misunderstand those directions. So there's left 3 and up 4. About like, yay. So the distance, the modulus, is the blue line right there. In order for us to make sense of a diagonal distance, though, we have to make it into a triangle so that we can use the Pythagorean theorem, which is, again, is just the distance formula, right? So I'll put a little right angle in there. What is the length of my bottom leg? Just 3. What's the length of my vertical leg? 4. And we're going to use, again, the Pythagorean theorem. And we're going to say a squared plus b squared equals c squared. What's 3 squared? What's 4 squared? 9 plus 16 is? So I can then say that c squared is equivalent to 25. Therefore, c is equivalent to what? Perfect. Sometimes your absolute values come out as whole numbers when it was meant to be. I don't know if you remember this from Mr. Manlove's geometry class, but these 3 numbers, 3, 4, 5, they make what we call a Pythagorean triple. They're just certain numbers that always come out nice. Have you ever heard that before? A triple? Does anyone remember any other triples? I'll give you a couple more in case you see them. You might want to add these to your notes. So the most common Pythagorean triple is, of course, the 3, 4, 5. People use that all the time. Ask anyone who's in like the construction business or does any framing. They'll tell you that they use the 3, 4, 5 triple pretty regularly to force right angles. Another popular one is 5, 12, 13. Another popular one is 8, 15, 17. Another popular one is 7, 24, 25. And what's nice about triples, there's obviously infinitely many triples, but those are the most common ones that you'll see. What's nice about triples is that you can scale them up. And so if 3, 4, 5 is a triple, so is 6, 8, 10. You see what I did? I just doubled all the numbers. What would be the modified version of 5, 12, 13? Those are all triples. So on and so forth. Now, I'm going to show you the shorter way to do this, and then I'll be done. I'll shut up and get out of your way. So let's find the absolute value of 6 minus 4i. I don't expect you to draw a triangle every time. Of course, you know that I wouldn't ask that of you because that would take a lot of annoying work. And so what we're going to do is we're just going to, in our mind, we're going to think about it To get to the point 6 minus 4i, we would go right 6 and down 4, correct? So the legs of our triangle, we all agree, are 6 and 4. So you can actually bypass a bunch of the work and say, so I know at some point I'm going to have to do 6 squared because that's the sidey leg. And then I know at some point I'm going to have to add to it 4 squared because that's the uppy downy leg. And what was the last step? What was the last thing we kept doing when we were doing those diagonal liney ones? Say again? And then what? And then we square root them. So if I don't want to draw pictures and all that, I could just simply take my A value, square it, my B value, positive, negative, doesn't matter because I'm going to square it and then root that sucker. And that's how I find my absolute value. Super quick and easy. What's 6 squared? What's 4 squared? What's 36 plus 16? So the answer in its unacceptable form is root 52. How do we break down a root 52? Cuatro por trece. Sí. 4, 13. Como esto. All right, let's try again. You ready? Let's find the absolute value of 5 plus 12i. If you look up in your notes, assuming you wrote those triples down, that would help you for the record. This is a triple. Do you remember the completion 5, 12, 13? 5, 12, 13 is a triple. And if someone is nice enough to give me a complex number whose A and B parts are 2/3 of the first 2/3 of a triple, then I know that the answer is 13. Where it comes from is 5 squared and 12 squared added and rooted. What's 5 squared? What's 12 squared? Add them together, you get 169. Square root that, jackpot. Good? Anyone have any questions about that? That's what you're doing today. Your assignment today will be to graph complex numbers and then find the complex or find the absolute values of complex numbers. I will.